Hello guys, welcome back to our lecture 20. So in this recording, we're gonna take our last example this week, okay? Which is again sequence detector, same example, everything is the same. But now more circuit with T flip-flop. So when we solved this in the two records ago, it was Mealy circuit with T flip-flop. Now, same stuff, but more with T also, okay? And we're gonna comment on the result because now after finishing this example, we're gonna have two designs. Both are using T flip-flops, but one with Mealy and one with more circuit. So we can now differentiate between both. We can have an idea which is easier to implement, which is have more hardware resources, something of that sort. Okay, so let's start again by the state diagram. But remember here, it's a more circuit, not Mealy circuit. So let's refresh our mind with the state diagram of Mealy. It was two states. I'm sorry, yeah. It was only two states. State means no one's detected. Another state called one or more ones detected. Okay, when we receive one, we transition to the second state, and the output will be 0. If the state is 1 and we receive 1, we're gonna stay in the same state because now we received the 2 or more. Okay, and the output will be 1. If we receive the 0, we're gonna go back to the 0 state. 0 1 is detected. If we receive 0 while we are 0, we're gonna stay in the same, and the output will be 0. Okay. Now let's do the same, but with a more approach, more circuit. Remember, in a more circuit, the output is only dependent on the state. So here, Y is only a function of Q. The Q's, if you have more than one flip-flop. So with Mealy circuit, we have just one flip-flop. So let's try to use the same approach. I mean two states, S0 and S1. S0 means no one's detected. So the output in that state, regardless of the input, should be 0 because it's a more circuit now. But how about if we said that S1 is one detected? Oh, that's a problem. Why? Look, regardless of the input, we should determine Y in each state. In that state, if we use the same state, which is S1 of the Mealy circuit, which is that one here, which is basically one or more ones detected. Now we'll have a contradiction. Why? If we receive one, just one, I mean, okay, Y is 0. Okay. But if we receive 2 or more, we're still with the Mealy circuit, we're still in the same state. It's 1. But the output will change and they become 1. So if we use the same state here with more, we will not be able to determine what output I should give. Because if I receive just 1, the output is still 0, should be 0. If I receive 2 or more, the state, the output should be 1. So I can't do that. I can't have a state that lead to 2 different outputs at the same time with more approach or more circuit. Okay, so what we're gonna do here is that we're gonna define another state. So S2, and S1 would mean one is detected. And in that case, still Y is equal to 0. And S2 now would mean 2 or more. I can't do that because when I say 2 or more, I conveniently I can put y is equal to 1. 2 or more ones detected. And in that case, y is equal to 1. By the way, more with that approach here is an easier one to implement and not, easier to analyze, we can say, or to think of. I mean, you can find easily the states if you are using more approach or more circuits, because it's determined. You don't need to know the input. Just assume the cases, okay, and based on each case, you're gonna know the output for sure. But as you see, more leads to more states. And what is the problem with that? More states means, let's see. Now you have three states, okay? We said that each state should have its own, outputs. So if you have 2 states, you can have just one flip-flop because its output should be either 0 or 1. So one state is one flip-flop can represent the 2 states. But here we have 3 states. So basically one flip-flop is not enough. And you need at least 2. Because if you have 2 flip-flops, you will have 2 states, 2 outputs, 2 Qs, Q and QB, for example. So they can represent 4 states, 0, 0, 0, 1, 1, 0, 1, 1. Here we just need 3. Okay, so we need here 2 flip-flops. That's the basic, problem. Or if we say pros and cons, that's a disadvantage. Because here we used 1 flip-flop, 1 T flip-flop. Here we are using 2. That means more resources, more hardware, more power consumptions, more complexity, of course. So let's now do the state diagram. 3 states, S0, S1, S2. If I am in S0, that means I received no ones, so y is 0. And if the input is 0, still I receive 0 ones, so I'm gonna stay in the same state. But if I receive 1, I should go to S1. That means we received 1, 1, exactly 1. And if I am in S1, the output for sure is 0. Now, if I am in S1 and I receive the 0 again, that means 0 number of ones received, so I'm gonna go back to S0. But if I receive 1, I should go to S2. That means I received 2 ones. Now, if I am in S2 and I receive 1, that means 2 or more ones detected. So I should stay in the same state. And whenever I'm in S2, y is 1 for sure, regardless of the input. And again, if I am in S0 and I received 0, I should go to S0 again. That means 0 ones detected. Okay. That's basically, guys, the state diagram. Okay. Now we just need to assign each state a code, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so you have 4 codes out of 2 bits. Do whatever you like. You can say that S0 is 1, 1, or S1 is 0, 0, whatever you like. So let's choose S0 equal to 0, 0. S1 is 0, 1. S2 is 1, 0. But again, this is a choice. This is your choice. It is 1, 0. Okay, that's basically the state diagram. So let's check the output, the solution. I'm not sure if it's gonna be clear. Yeah, let's remove. Yes, it's basically the same as what we have done. So S0, S1, S2. Okay. Just an example, if we are on S0 and we received 1, we go to S1. That means 1, 1 is detected. And then if we are on S1 and we receive 1, we go to 1, 0, S2. 2 1s are detected. Then if we are on S2 and we received 1, that means more than 2 1s are detected. Okay. Good. Let's check now or build. Since we could build the state diagram, we can build easily the state table. Since we have the state diagram, we can build easily the state table. Remember now we have 2 flip-flops. So we have QA and QB. This is basically the present state. And we have the input X. And we have, you know, the next state. QA plus, QB plus. And we have our output, Y. And of course, we need to determine the input function of each flip-flop, TE and TB. These 3 variables can take 8 combinations. 0, 0, 0, 0, 0, 1, 1, I'm sorry, 0, 1, 0, 0, 1, 1, then 4 ones here, 0, 0, 1, 1, 0, 1, 0. Okay. And here is again the state diagram. 0, 0, 0, 1, 1, 0. We go here when we receive 1. We stay if we receive 0. We go back if we receive 0. We go to this one if we receive 1. We go here if we receive 0. We stay if we receive 1. The output here is 0. The output here is 0. The output here is 1. Really simple. Okay. Now, let's check. When the current state or the present state is 0, 0, which is that one here, and we receive 0, we stay in the same state. And the output is all the time 0. If we are in 0, 0 again, but we receive 1, we go to 0, 1. And the output is, when we are in 0, 0, the output is 0. So we can determine the output just without looking at QA plus and QB plus. For example, 0, 1, the output is 0. 1, 0, the output is 1. And now we have unused state. And we're gonna see at the end what we're gonna do with them. So let's keep, because this is unused state. So QA and QB are 2 bits. They have 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. We used 0, 0 for S0. We used 0, 1 for S1. We used 1, 0 for S2, but we didn't use 1, 1. And here is, you know, the idea. We're gonna see it, but you can, for example, use what we have done before. Use don't cares. Okay, good. So let's keep it to the end. When we are in state 0, 1, that one here, and we receive 0, we go back to 0, 0. When we are in 0, 1 and we receive 1, we go to 1, 0. When we are 1, 0 and they receive 0, we go to 0, 0. But if we receive 1, we're gonna stay at the same state, 1, 0. Okay. TA and TB. We said that TA is equal to, or T, you know, in general, T in general, not just TA or TB, is equal to QA XOR QA plus. We did use this or drive this, you know, when we studied this circuit using Mealy. So just look at QA and the QB and QA plus. So if you have even number of ones, this is 0. Odd number of ones, this is 1. So we have 0, 0 again, 0 again, then 1, then 1, then 0. Okay. Then for TB the same. QB XOR QB plus. QB QB plus 0 0. So this is 0. 0 1, this is 1. 1 0, this is 1. 1 0, this is 1. 0 0, this is 0. 0 0, this is also 0. Now, what we should do with the 1 1 state? Okay. See, so here you have two options. Either don't cares, or the better approach is to lead the system or reset the system to one of the known states. So, what does that mean? Let's assume that if I am in 1 1 and I receive 0, I go to 0 0, and I receive 1, I also go to 0 0. What does that mean? That means that if for some reason, of course, this shouldn't happen. For this, once this circuit is operating, you should see either 0 0, 0 1 1 0 at the output of the flip-flops. You shouldn't see 1 1. But for some reason, noise, for example, okay, and there was 1 1 at the outputs of the flip-flop, then you need some technique to reset the circuit to a known state. We know that if we are in 0 0, we know how to move to other states. Okay, that's basically why I choose 0 0. You can choose S1 or S2. You can put that if I am in 1 1, I'm gonna go all the time to 1 0 or 0 1. Okay, and of course it's better to go to the reset state. Good. Now you should also choose some output, although you can just assume don't care here. So let's put again 0 0. And now TA and TB, let's check also. See, TA is again QA and QA plus 1 0, this will be 1. And QB 1 and 0, this is also 1. 1 1 as well. Okay, that's basically how to choose the unused state. This unused state shouldn't happen, although if you have noise or something out of hand, basically, then you know what the circuit should do. It should reset itself to one of the known states. Okay, let's build in the Carnot map and see the equations. So let's start, for example, by Y. This is QA, QB, and X. So you have 4 zeros, then 1 1, 0 0. So Y should be equal to QA, QB bar. That's basically Y. Let's do TA. So 0 0, 0 1, then 1 0 1 1. So you have two groups, this group in here and that group. So TA should be equal to, this group is XQB plus this group is QA X bar, QA X bar. Okay. Now, finally, TB, you have 0 1 1 1, then 0 0 1, 1. So you can take these together and this group as well. So TB is equal to, this guy will give us QB plus this group in here should be X QA bar, X QA bar. Okay. Okay, so let's check the solutions. So let me so TA is QA X bar plus QBX. So QA X bar, QBX, that's right. Let's check QB. It is QB plus QA bar X. That's also right. Let's check Y. Y is QA QB bar. Where is Y? Yes, QA QB bar. So that's also right. Don't, try to compare the two tables together. It's a cumbersome. If the table is right or correct, then the equations should be correct. Okay, so let's remove the mess here. Okay, let's now build the circuit. So you have T flip-flops. Let's do it, TA, TB, it is QA, QB. So TA is QA X bar, QA X bar, so here is X, for example. Or QBX. Here is QB. Here is X. Okay, then TB is QB. Here is QB. So we have also an OR gate. Plus or QA bar X. So remember, you have already QA bar. So here is QA bar. Here is X. It is QA bar. What is Y? So Y is an AND gate. It's really simple. QA, QB bar. That's basically Y. So let's check our implementation in here. And looks like we are, yes, we are good to go. Yeah, that's right. Okay, guys. Now, the $1 million question. Which is better than which? Mealy or more? Okay, so let's compare, the two implementation in this last slide in here. Okay, so we have here the two approaches, the two results when we design with mealy and when we design with more. This is a design of mealy. This is the design of more. Okay, it's very clear that the design with more or more version of this design, has more hardware resources. It's more expensive. It more power consumption. Okay, and why is this? The problem with more is that you may, it's not all the time, you may need extra states. So if you are designing a circuit using the two approaches, you either get the same states here and here in more and mealy, and in that case the hardware will be comparable. But some cases you might need more states with more circuits than the mealy. At that time you're gonna have more hardware used. Okay, so that's basically the big difference. Another also difference but we're gonna study it in the if we have time in the following weeks, is that the idea that the output here is dependent on the queue, the state, and the input in Mealy circuit might lead to some glitches in the output that might trick the user. So for example, the stable output should be 0, for example. But you might have a glitch that y become 1, although it will go back to 0. But the user might consider this 1 as the final state or final value for y, which is wrong. I know it's not that clear using this example, but if we have time in this course, we're gonna see a proof, we can say, an example that shows that such a kind of problem. Okay, guys, that was basically the sequence detector using 3 designs: T flip-flop with Mealy circuit, D flip-flop with Mealy, and we see that the change of the flip-flop might reduce the hardware cost, and the sequence detector with more circuit and the T flip-flop, and we see that using more, we have more states, so we have more hardware. And that was basically a problem for the Moore approach. Okay, guys, thank you very much for watching this video, and see you next week. Bye-bye.